Hello everyone, I am Osamu Kada. In the previous video, we proved the Cayley Hamilton Theorem from the approach using the notion of matrices whose components are polynomials in the matrix. Today, I am going to prove the theorem from the approach using the notion of R module. Here, R is a polynomial ring RT or MNRT, the matrices whose components are polynomial rings. The theorem states as follows. Cayley Hamilton Theorem. Let A be a n times n matrix whose components are real numbers. Instead of real numbers, we may take any commutative ring R. Let P of T be the determinant of Ti minus A, the characteristic polynomial of A. Here I is the identity matrix, and P of T is the element of polynomial ring RT. Then we have P of A is equal to the zero matrix. Now we give a proof. Let P of T be the Ti minus A transposed. This is a matrix whose components are polynomials in T. Then determinant B of T is the determinant Ti minus A transpose, which is equal to determinant of Ti minus A, and it is equal to the characteristic polynomial of A. Let B of T tilde be the adjunct matrix of B of T. Then we have B of T tilde times B of T is equal to determinant B of T times I, which is equal to P of T times I. Let R be the polynomial ring RT, and B be the Rn, n-dimensional vector space, and consider B as an R module by the following. For the polynomial f of t, which is equal to summation from I equals 0 to m of the ai times t to the I, and for the f of t times x is defined to be f of a times x, which is equal to the summation from I equals 0 to m of the ai times capital AI to the I x. Here we recall the notion of R module. Let R be a ring and M be an abelian group. For the element R in R and X in M, R times X in M is defined, and M is a left R module if the following conditions are satisfied. Rs times X is equal to R times S times X, and 1 times X is equal to X. And this says that R acts on M, and R times X plus 1 equal to Rx plus Ry, and R plus S times X is equal to R times X plus A times X. In our case, R is a L times T to GL, and S is a BM times T to GM. Rsx is equal to L T to GL times BM times T to GMX. And this is equals to L times BM times T to the L plus M times X. And by definition, T to the L plus times X is equal to A to the L plus MX. And R times Sx is equal to L to the L times BM to the T to the MX. And BM times T to the MX is defined to be Bm times A to the mx, and multiplying L times T to the L from the left, this is defined to be L times A to the L times Bm times A to the mx, and this is equal to L times Bm times A to the L plus mx, and this is equal to this, which means that this is equal to this. So Rsx is equal to R times Sx. So the condition 1 is satisfied. And 1 times x is defined to be A to the 0x, and A to the 0 is the identity matrix, so Ix is equal to x. So the condition 2 is satisfied. Let R prime be the MNR, the matrices whose components are polynomial, and consider V to the n an R prime module as usual, that is matrix times vector. Since B of t which is equal to ti minus a transpose, is an element of R prime, and the vector e1 to em is in V to Gn. Here e1 to en is a canonical basis of Rn. So we can multiply e1 to en from the right to the B of t. And this is equal to ti minus a transpose times e1 to en, and ti is equal to this diagonal matrix and a transpose times e1 to en, and t1 to ten is the first term, and the second term is e11 e1 plus, and so on to en1 en, and so on to e1n times e1 plus, and so on to enn times en. And by definition, t1 is equal to a1 and tn is defined to be aen, and this is equal to a11 to an1, which is the first element, and e1n to enn, and this is equal to the first column vector of A, which is equal to a1. The first element is equal to 0 vector, and so on to, and this is equal to the last column vector of A, which is equal to an. So the last element is equal to 0, which means that b of t times e1 to n is equal to 0. Since b of t tilde times b of t is equal to pa of t times I, and multiplying e1 to n, and b of t times e1 to n is equal to 0, b of t times e1 to n is equal to 0. So this equals 0 means that this is 0, and this is equal to p of t times e1 to pa of t times en, and this is defined to be pa of a times e1, and this is equal to pa of a times en. So it is equal to 0 means that pa of a is the 0 matrix. Consider the following example. Let it be this matrix. That is, first column is 2 times e3, and second column is 0 vector, and third column is a minus e1. Then b of t is defined to be ti minus a transpose, which is equal to this matrix, and the adjugate matrix b of t tilde is equal to this matrix. For instance, this element is defined to be deleting this and 0 plus 2 times t, and so on. The characteristic polynomial p of t is equal to determinant b of t, which is equal to t cubed plus 2 times t, and p of a is equal to a cubed plus 2 times a. Then b of t tilde times b of t is equal to this matrix times this matrix, and t squared times t plus 2 times t times 1 is equal to t cubed plus 2 times t, and t01 and t01 is equal to 0, and minus t times t plus t squared times 1 is equal to 0, and so on. So b of t tilde times b of t is equal to this diagonal matrix, and b of t is equal to ti minus this matrix. So multiplying e1 into e3, we have t1, t2, t3 minus 2 times e3, 0, and minus e1. And t1 is defined to be a1, and t2 is equal to a2, and t3 is equal to a3, and a1 is equal to 2 times e3, and a2 is equal to 0, and a3 is equal to minus e1. So this is equal to 0. So that b of t tilde times b of t times e1 to e3 is equal to 0. And b of t tilde times b of t is equal to this matrix. And multiplying e1 into e3, we have t cubed plus 2 times t e1 and this is defined to be a cubed plus 2 times a times e1, and so on. And this implies that a cube plus 2 times a is equal to 0 matrix, and this is equal to PA of A.